For the final part of organic chemistry, we need to look at two remaining homologous groups or families. We're going to look at the alcohols and the carboxylic acids. So alcohols are a family of organic compounds which have one big thing in common. They all have the same functional group. The functional group you find in an alcohol is an oxygen atom joined onto a hydrogen atom. This is sometimes referred to as the OH group. Every alcohol must have an OH group. Like the other families of homologous series we looked at before, you need to know the first four members of the alcohol family. You need to know their names, their structures, their formulas, and their states at room temperature. This is the first alcohol. It has got one carbon. There's an OH group directly attached to that carbon, and the remaining bonds are made up by hydrogen atoms, so the carbon has 4 bonds in total. Because there's only one carbon atom in it, it gets the prefix meth, and that gives us a molecule methanol. The second alcohol has got 2 carbons in it. It doesn't actually matter which carbon you put the OH group on because it actually is equivalent whichever way you put it. Each carbon still has 4 bonds, and that gives you the molecule ethanol. Now the final 2 alcohols are very similar looking. They both have got 3 carbons, and the only difference between them is the position of the OH group on the chain. With propan-1-ol, the OH group is on an end carbon. I've drawn it on the right, it could also go on the left, it wouldn't really matter, but it's not in the middle. In the second 3 carbon alcohol, propan-2-ol, you see the OH group is attached to the middle carbon, which is a different position and a different molecule than when it's attached to the end carbon. The way we distinguish them, because they both have 3 carbons and therefore get the name prop, is just by the number in the name. So propan-1-ol, it's on the first carbon or end carbon. Propan-2-ol, the OH group is on the middle carbon. I've written in the formula of each alcohol here. What you notice is that we put the OH group at the end of the formula and we kind of split up the H's so that one H belongs with the oxygen. That makes it really clear when you're looking at the formula that you are actually talking about an alcohol because you see the OH group at the end by itself. The final thing I've written in by their structures is the state they are at room temperature. Luckily it's pretty easy to remember this. They're all liquids at room temperature. The next thing is a general formula. Now we've seen this for other homologous series or families in this topic. This is kind of like the code formula, and for alcohols it's just CnH2n+1OH. That will give you the formula of any alcohol if you know the number of carbons in the alcohol. The second thing we need to know about the alcohols is the method of preparing them. To prepare an alcohol just means to make it in a chemical reaction. You need to know 2 different methods for making ethanol. Ethanol is the main, most useful example of an alcohol. The first reaction we'll look at is the reaction with steam. Now this is a reaction we've already looked at in the alkene section of organic chemistry. If you take an alkene ethene, which got 2 carbons, and you react it with water in the form of steam, that will actually turn the alkene into an alcohol, so ethene will turn into ethanol. You just need to know the equation for this process. So C2H4, which is ethene, plus H2O, which is water, but we're using it in the gas form, so it's steam, goes to C2H5OH, which is the formula of ethanol. The second method of making ethanol is by fermentation. This is a process used when making alcoholic drinks like beer and wine. Basically, you react sugars like glucose with yeast and they do anaerobic respiration to produce alcohol. The way to define fermentation would be to say it is the breakdown of sugars to produce ethanol. Now you don't need to know a symbol equation of this reaction, a word equation will do. Glucose reacts to break down to form ethanol and carbon dioxide. There's 3 conditions for this reaction you need to know about. The first is that you need a microorganism yeast to do this fermentation process for you. You need warm temperature conditions. Now warm means anything up to but slightly below 37 degrees C. Above 37 the yeast will actually break down and die, so a warm temperature but not too warm. Final condition is an absence of air. You want these yeasts to undergo an anaerobic respiration and not aerobic respiration. Anaerobic, which means without air, causes the yeast to make ethanol in this process. The final thing we need to know about the alcohols is one main chemical reaction of them. Alcohols are quite good fuels. They're quite good at doing combustion and burning. Just like before, all we need to know is examples of complete combustion, where you make carbon dioxide plus water, or incomplete combustion, where you make carbon monoxide plus water. So for an example of complete combustion, we've got ethanol here, C2H5OH, plus O2, because remember combustion is just the reaction with oxygen. If it says in the question complete combustion, you can assume you're going to form carbon dioxide plus water. Now to balance it, we'll do it the same way we did for the earlier combustion equations. It's easiest if we balance the carbons first, hydrogen second, and oxygens last. So carbons first, there's 2 carbons on the left hand side, only 1 on the right hand side. Let's put a 2 in front of the CO2. Now for the hydrogen, just be careful you make sure you count all of them on the left. There's 5 H's here plus an extra one here, so there's 6 on the left overall. We've only got 2 on the right overall. So let's multiply the H2 up by 3 to get to 6 on the right hand side. Now finally the oxygens, again we have to be careful here because there's oxygens in lots of places. On the right we've got 2 CO2, that gives me 4 oxygens from this part, plus 3 further oxygens from the H2O. That gives you 7 in total on the right hand side. On the left hand side we've got O2 here, which is 2 oxygens, but we also have this extra oxygen in the alcohol formula, so there are 3 on the left. The easiest way we can get both sides to be equal would be to multiply up the O2 here by putting a big 3 in front of it. Now if you think about what that does, that multiplies this O2 up to give us 6 oxygens. If we add on our extra one here, which gives us the 7th, that matches up with the 7 on the right hand side. Now let's look at an incomplete combustion example. We're going for a slightly different alcohol this time. We've gone for one of the propanols. I'm not sure if it's propan-1-ol, propan-2-ol, doesn't really matter. If it's incomplete combustion, it's still reacting with oxygen, but we're assuming it's in limited oxygen conditions, and that causes us to make carbon monoxide and water. However, we balance it exactly the same way. Let's do carbons first, big 3 in front of the CO. Then we'll do H's. There's 8 on the left, we need 8 on the right. That means big 4 in front of the H2O. Now if we look at the oxygens on the right hand side, we've got 7 in total, 3 from the CO and 4 from the H2O. We need 7 on the left as well. We've already got 1 here, therefore we just need 6 extra ones from this O2. That means we need a big 3 in front of the O2 as well. The final section of organic chemistry we need to look at is the carboxylic acids. They are a 4th and final homologous series or organic family of molecules. Now just as the alcohols, the carboxylic acids have got their own unique functional group that makes them carboxylic acids. Their functional group is quite complicated looking. There's 4 atoms involved in it. It's a carbon double bonded to an oxygen and then single bonded to a separate oxygen which is called an H on it. We put that together and call that the COOH group. Now that group is much easier to understand if you see it drawn out. So let's look at the 4 examples of carboxylic acids you're meant to know about. Like every family, the simplest example only has 1 carbon in it. So we put 1 carbon in this first example. It's got the COOH functional group. This carbon therefore has got 3 bonds already. It just needs 1 further bond to make it happy. That's why our 4th bond is to the hydrogen. Because it's only got 1 carbon, it's given the prefix meth, and that gives us methanoic acid, the simplest carboxylic acid. The second carboxylic acid isn't much different. It's just got an extra carbon on the end. So we see 2 carbons in ethanoic acid. The carbon here in the end needs 4 bonds. That gives us these 3 extra hydrogens, which are slotted on at the end of the molecule. Ethanoic acid is a very common molecule. It's more commonly known in everyday life as vinegar. The final 2 carboxylic acids aren't much different. Propanoic acid has got 3 carbons in the chain. Butanoic acid has got 4 carbons in the chain. The only thing you need is a COOH group on the end of the chain, and every other carbon has a normal 4 bonds. Now in terms of their formulas, if you had to write them down, again we try and keep the COOH separate and at the end of the formula to make it really clear we're talking about carboxylic acid. Everything else, carbons and hydrogens, just gets added up on the left hand side of the formula. Let me show you. So I've written all the formulas down here. If we just look at one for an example, if we look at propanoic acid, we've got the COOH, which is the important functional group part on the end of the chain. Before that COOH, we've got 2 carbons and 5 hydrogens. They just get written down at the start of the formula, C2H5COOH. We can put these formulas together just like we did before to get the general formula of a carboxylic acid. It's not too different to the general formula of an alcohol, CnH2n+1COOH. Lastly, for their structures, we just needed their state at room temperature. Kind of like the alcohols, they are all liquids at room temperature, the first 4. Now for a couple of properties of the carboxylic acids. Kind of unusually, and in contrast to the other organic families we've looked at so far, carboxylic acids are not very good at burning. They do not combust easily. The second thing about them is, obviously the clues in the name, carboxylic acids. All of these carboxylic acids do behave like weak acids. And that's a little reminder of the definition we had back in year 11 of a weak acid. For something to be an acid, it needs to be able to ionize in solution to give off hydrogen ions. If they're a weak acid, they only do that partially, not 100%. So weak acids partially ionize in solution. So to give you a concrete example of that, here we've got the formula of ethanoic acid, CH3COOH, acting like a weak acid. This is what ionizing means. It's split apart into two separate ions. This H plus ion here is what makes it an acid. Anything that is an acid must have that H plus ion given off in solution. The remainder here, this is kind of like the leftover part of the acid. This would be referred to as the ethanoate ion. And we'll have to use that ion whenever we're doing these chemical reactions we'll look at the bottom of this page. And that's the only remaining bit we've got to look at for the carboxylic acids. You need to know 3 main reactions of carboxylic acids, which are kind of in common with the reactions of acids we looked at back in year 11. The first reaction we look at is with metals. If you remember back from year 11, a metal with an acid always forms a salt plus hydrogen. So if we try to give an example using a carboxylic acid, you need to be able to know the name of the salt produced in these reactions. So we've gone for magnesium being the metal, ethanoic acid being the acid. For the salt, the first word of the salt comes from the metal, so we're going to go for magnesium. The second word of the salt comes from the acid. Ethanoic acid will give you ethanoate as a salt ending, and then hydrogen is just hydrogen. And that gives us our complete word equation. Now you do also need to know the symbol equations of these reactions, which can be a little bit tricky. The left hand side isn't too bad because those are both formulas we should know. Magnesium, just off the periodic table, is Mg. Ethanoic acid, you're meant to know its formula anyway, which gives us CH3COOH. Now for the formula of the salt, magnesium ethanoate, we need to do a swap and drop to get its formula. Now magnesium, because it's in group 2, gives us an Mg2 plus ion. Ethanoate should be found on the back of your periodic table. I've got mine here. If you look on the back cover of it, you'll see in the negative ion table ethanoate here. And that gives you the formula of the ethanoate ion that you could use for a swap and drop. Now if I just show you that here, the swap and drop involves the following step. We write down our 2 ions we need for our swap and drop, and we look at the numbers in front of the charge. So for Mg we've got 2, and then CH3COO we've got a 1. We swap those numbers over and we drop them down. Now because we're multiplying up ethanoate by 2, we need to protect it with brackets. But the magnesium just has 1, it's left as it is. Now the final twist here is, normally when we're writing the formulas of these salts, we put the metal actually on the right hand side. The simple reason for that is the negative charge in this big long ethanoate ion is actually on the oxygen, and that's going to be the bit which is attracted to the magnesium. So we normally write the magnesium over to this other side. And that is our finished formula. So that's all our formula written in. We just need to balance it to get everything perfect for this equation. Now if you look at what we've got on the right hand side, we've got quite a lot of carbons, hydrogens and oxygens. All we need to do here actually is just add a big 2 in front of the ethanoic acid to get all those carbons, hydrogens and oxygens balanced out. Reaction number 2 is with metal carbonates. Whenever you react a metal carbonate with an acid, you make a salt, carbon dioxide plus water. Let's look at a quick example. Gone for calcium carbonate as my metal carbonate, gone for a different acid, methanoic acid. The salt here is similar to one we had before. The first word comes from the metal, we'll go for calcium. The second word comes from the acid, methanoic acid. We take from that methanoate, which leaves us calcium methanoate, carbon dioxide plus water. Now I've just written this symbol equation down, but it follows all the same steps we did in our first example. For the swap and drop, we just need 2 of the methanoate ion, remember that's found in the back of your periodic table, with the calcium at the end. Everything else is semi-normal as a formula. Balancing, we put a big 2 in front of the methanoic acid. Final reaction is with a metal hydroxide, otherwise known as a base. From year 11 we have that a base plus acid goes to a salt plus water. The example I've gone for is sodium hydroxide, which is an example of a base. Butanoic acid giving us sodium butanoate plus water. Now this final example, because sodium is in group 1, for our swap and drop over here, it's Na plus C3H7COO minus. Because it's 1 plus 1 minus, we don't actually need brackets in this one because nothing is being multiplied up by 2.